In this video, we're going to talk about Cauchy sequences, and in particular, we're just going to introduce what they are. We are familiar with convergent sequences. We know that a sequence converges. Say the sequence is P1, P2, P3. It converges to P. So these are all points in some metric space E. Converges to P if given any positive number epsilon, there exists some n such that for all integers m and n greater than capital N, the distance between P and P sub n is less than epsilon. Oh, no, for all little n greater than capital N, the distance between P and P sub n is less than epsilon. So you could have, for instance, a sequence of points that converge to a point that is not any of the terms in the sequence. So for instance, you can have something like P1, P2, P3, etc. up to, well, P is not in the sequence, but it's some point. So to introduce the concept of a Cauchy sequence, suppose that P is not equal to any of the PI's. Okay. So these points, the PI's and P, are in some metric space E, right? The points PI and P, okay, are all in some metric space E, right? All of these points are in some given metric space. Now, suppose we define a new metric space E prime to just be E, except you remove the point P. And so this is a subset, and you give it the metric space structure induced by the metric space structure on E. Okay, well, since P is not any of the PI's in this scenario, the PI's are still elements of E prime. So each PI is still in E prime, which is a subset of E, because the only point you removed was P. And we suppose that P is not equal to any of the PI's. However, even though you have the same sequence, P1, P2, P3, this sequence does not converge in E prime. Okay, why not? Well, the idea is that it converges to P, and P is not an E prime. That's the idea. So why not? Well, suppose that it did, and it converges to some point Q in E prime. Well, E prime is a subset of E, so the PI's converge to Q, and these are all points in E, right? But we know that the PI's converge to P in E. And by the uniqueness of limits, P must be Q. Well, that's a contradiction, because, so this is a contradiction. Why is this a contradiction? Well, because P is not an E, and Q E prime, I mean, and Q is in E prime. So what this is saying is, if you have a sequence and the limit, so it's a convergent sequence, and the limit is not any of the points in the sequence, okay, then you define a new metric space where you just remove that point, then all of a sudden the sequence no longer converges in that metric space. So what this is saying is that the convergence of a sequence depends on points that are sort of outside your space. Now that kind of makes sense. Outside of the sequence, I mean. So because of that, convergence in some sense is not really a property of the sequence itself. It's a property of what other points are possibly in your metric space. So what we want is a notion that only refers to the points in the sequence. Only refers to the sequence itself, not limits of the sequence. Remember, the limit of a sequence may not be a point in the sequence. So this leads us to the notion of a Cauchy sequence. So this sequence, P1, P2, P3, will be a Cauchy sequence in E prime as well as in E. Okay, so intuitively, we think of the points as bunching up together, right? The points are getting arbitrarily close, but we want a notion of that does not depend on the actual limit P. So that leads us to the following definition. So the definition is a sequence of points P1, P2, P3 in a metric space E is a Cauchy sequence if for all epsilon greater than 0, there exists some positive integer n such that for all little m and n greater than capital N, the distance between p sub m and p sub n is less than epsilon. So what this is saying is that given any possible distance, epsilon, the points in the sequence eventually are all within epsilon of each other. Notice that we're talking about the distance between p sub m and p sub n. Those are points in the sequence. So this definition only makes reference to points in the sequence. That's different than what it means to converge, because in order to talk about a sequence converging, okay, you have to refer to what it converges to, some point P, and the distance is the distance between P and the P sub n. So in the definition of convergence, we're referring to some point that might not be in the sequence. Whereas in the definition of Cauchy, you are only talking about points in the sequence. That's the big difference between the concept of a convergent sequence and the concept of a Cauchy sequence. Of course, these concepts are not exactly the same, but they are related, and in future videos we'll talk about how these concepts are related.